Hello and welcome to today's video. In this video, we're going to talk about Taylor polynomials. Now, you will remember that we've discussed tangents of function graphs already. Basically, a tangent is a polynomial of degree 1. The properties of defining a tangent are the tangent has the same function value as the function that it approximates at a given point x star. And at that point, it also has the same first derivative. It has the same slope as the function that it approximates. And of course, a possible question is, how can you extend that to polynomials of higher degree if you require that in addition to the function value and the first derivative, also higher order derivatives at that point should have the same value? What do you gain from that? How would that approximation look like? Is it useful? And what can we say about the properties, the approximation properties? And that's the basic idea of Taylor polynomials. So to recap, we know about the tangent of f already. And that tangent can be seen as a polynomial of degree 1 that has the same function value and also the same first derivative. As the function f that we're trying to approximate at the point x star. And of course, a general polynomial of degree 1 is given as some constant a0 plus a1 times x. So basically, we have two constants, a0 and a1, that you want to determine. And determining those, of course, requires that you fix the value of the polynomial at two different points, or you fix the value of the polynomial at a certain point, and you fix the derivative of the polynomial at that point. So we can have these two things that we require from our approximation: the function value and the derivative, and those will serve to determine these two constants here. And then the task at hand is to determine a polynomial of higher degree, of degree n, with the same properties, but extend it to higher order derivatives. And with this here in mind, we can then go up to the nth derivative at that point. So we'd like to determine a polynomial of degree n that has, again, the same function value as f, and also the same first, second, and so on up to the nth derivative as f at a point x star. And the idea is to have a local approximation, local at x star of the function f. Now, let's see how such a polynomial would look like. To make things a little easier, we're going to write the polynomials in a form that is a little different from what we just saw. We're going to center them around that point x star. So we're going to write polynomials centered at x star. And the way to do this, well, will become clear in just a second. We start systematically with the polynomial of degree 0, P0 we'll call that. And for that polynomial, we want that it is equal to the function value of f at the point x star. Now, a polynomial of degree 0 basically has the form a0 and nothing else. And we would like to have p0 at x star equal to f at x star. So that means we'll have to choose a0 as f at x star. So what we get here effectively is p0 of x is f at x star. Now in the next step, we'll extend that to a polynomial of degree 1. We did that already, but just to recap that. Again, we want that polynomial to agree with f at the point x star in function value. So we'll start it in the same way, f at x star. And then we add a term, and the term will have the form a1 times x minus x star. And this here is what I mean by centered around x star. Instead of writing a1 times x, we write a1 times x minus x star. a1 minus times x star is just a constant that we subtract here, so that changes the constants just a little. The upside of this is that p1 at x star will evaluate to f of x star because this term will simply vanish. And that way we can reuse what we already knew. We can just reuse our p0 and add a term that vanishes at the point x star. So that's the whole idea here. So the only thing we have to make sure, in addition to what we have already done, is that the first derivative is equal to that of f at the point x star. So we know already that p1 of x star is equal to f of x star. That's fine. Now for the first derivative, let's compute that. That first derivative is simply a1. And we want that to be equal to f prime at x star. Well, what we have to do is, of course, we have to choose a1 equal to f prime at x star. So what we get here is p1 of x is equal to f of x star plus f prime at x star times x minus x star. And that is, of course, the functional description of the tangent that we have already derived in one of the earlier videos. Now, let's go on to higher orders. Hopefully that becomes more interesting now. So let's start with P2 here. Now, P2 of x will continue in the same way. We'll reuse our P1. So we just copy the first part here. And then we'll add one more term, and that term has the form a2 x minus x star squared. And again, we use this centering around x star, because if we substitute x star into P2, then this term will vanish along with this term. So what remains is just the P0 part, and that's already tuned correctly. And for the derivative, if we take the first order derivative of that term here, then as you can probably see, this of course will vanish, that's a constant. This will remain, but that will vanish. And here we'll still get one x minus x star term. We'll make that explicit in just a few seconds. So the idea is that in the first order derivative, again, this part will be 0 at x star, so it won't matter. The only thing that will matter is this part here, and we have already determined that one correctly. So let's make this explicit. Again, P2 of x star is, of course, f of x star, because these two terms will simply vanish at x star. p2 prime of x is equal to, let's see, this term here vanishes. Here, just the f prime at x star will remain. And for that term, we'll get 2a2 times x minus x star. So that means at the point x star, this second part will again vanish, and we're left with f prime of x star. And again, that is the point of this centering technique here, right? So we can reuse what we already know. So that's what we had already. Now for determining MA2, we'll need to have a look at the second order derivative. So let's do that. P2 double prime of x. We take this here and compute one more derivative of that. Then this part will vanish, and here we just get 2a2. So that's 2a2, and we want that to be equal to f double prime at x star. So that means we need to choose a2 to be f double prime at x star over 2. So that's a little different from what we've seen before. Now we have this factor over 2 here. And of course that comes from the repeated differentiation of that part, including the square here in the first part. So what we get ultimately is the following P2 of x is equal to f of x star plus f prime of x star times x minus x star plus f double prime of x star over 2 times x minus x star squared. And before we think about the general formula, let's do one more step here. Let's have a look at P3. And again, we just copy what we know already. And we can do this due to this centering technique. And then we add one more term, and that's going to be a3 x minus x star to the third power. And I hope you'll be convinced that the function value, of course, will work. The first derivative will have the desired value, and the second order derivative will have the desired value. So let's just look at the third order derivative. So P3 prime of x, that is f prime of x star. Oh, there's a square missing here, sorry. Plus f double prime at x star times x minus x star plus 3a3 x minus x star squared. Then one more step, fp double prime will then be f double prime at x star plus 3 times 2 times a3 x minus x star. And finally, p triple prime will be 3 times 2 times a3. And if you want that to be equal to f triple prime at x star, then that means we'll have to set a3 to f triple prime at x star divided by 3 times 2, or f triple prime at x star divided by 3 factorial. Yeah, because what you can see here is this factor here, this factor that comes ultimately from this exponent. And in each differentiation step, we take the current exponent, reduce it by 1, and put that current exponent in front of that factor here. So we get 3, then we get 2, then we get 1 in the next step formally. So if we had a polynomial of degree 4, then for that fourth degree part, we would get 4 times 3 times 2 times 1 in the end. So what happens here is basically that factor belonging to the polynomial part of a certain order is always the corresponding derivative of that order divided by the order factorial. Right? That's going to be the general formula. Let's write out P3 explicitly before we do that. So that is f of x star plus f prime of x star times x minus x star plus f double prime at x star over 2. And of course, 2 is the same thing as 2 factorial. So we could write it in this way. X minus x star plus f triple prime at x star over 3 factorial x minus x star to the third power. And I forgot again the second power here. And to make things a little more consistent, you could also write this here. Instead of f prime of x star, you could also write f prime of x star divided by 1 factorial. Remember, 1 factorial is just 1, so that doesn't change anything. And to get even more consistency, I could even write that term here in that same form. I could write that as f of x star divided by 0 factorial. And by definition, 0 factorial is also 1. Right? It's the empty product, and the empty product is 1. Okay, so that is the consistent form of writing these. And now it's easy to see what the general formula will look like. And that general formula is called the Taylor polynomial of order n, or the nth Taylor polynomial of the function f. So let's define that formally. As usual, we want a differentiable function, so we need to start with an open interval. So let I be a subset of R, and let that be an open interval. Let x star be in I. Let n be a natural number or 0. And let f be a function defined on that interval I. And what we want is that this function is n times differentiable on I. And then we can define what is called the nth Taylor polynomial of f at x star, or it's also called the Taylor polynomial of f at x star of order n. And that is defined as the following. The notation for this Taylor polynomial is a capital T for Taylor polynomial. Then we write the order here in a subscript, Tn. And we just write the function beside that. The variable for the Taylor polynomial, that's x. And the point, x star, where this Taylor polynomial is centered. So this is the notation for this Taylor polynomial. And that is defined as the sum from 0 to n. And each term of that sum is exactly of the form that we've just seen with our polynomials here. So that is the kth derivative of f at the point x star divided by k factorial times x minus x star to the power k. And furthermore, we'll be interested, of course, in the approximation quality of that Taylor polynomial. The idea is to get a hopefully good local approximation of a function. So we are also interested in the difference between the function and the Taylor polynomial at certain points. So this difference also gets a name. We'll call this the remainder. And also gets a symbol, the difference, that will be written as Rn at the point x, and that's simply defined as the function value f of x minus the Taylor polynomial of f around x star evaluated at x. This one here. So this is called the remainder. And as a remark, this Taylor polynomial does exactly what it is supposed to do, what we wanted it to do. It is the unique polynomial of degree n that coincides with f in function value and in derivatives up to n at the point x star. So let's put this as a small remark here. Tn f x star is the unique polynomial of degree n that coincides with the function value of f, which could also be seen as the 0th derivative at the point x star, the first order derivative, the second order derivative, and so on up to the nth order derivative at x star if we substitute x star for x, so at x equals x star. Now, of course, the interesting question here is what can be said about the quality of approximation? And we'll have a look at that question in one of the upcoming videos. And as usual, I hope I'll see you then.